So how many of you have had, before we get started, how many of you have had an Agile boot camp class? The lean, let's just say the Scrum class. Okay, how many of you have had the Agile boot camp lean class or Scrum to lean class? How many of you had no Agile classes whatsoever? How did you survive this long at Cerner with no Agile classes? So we have a sign-up sheet for classes later on. No, I'm just kidding. No, we do want to get you through some of those classes, but some of the slides and the concepts we talk about today do assume at least a working knowledge or an understanding of what Agile is. So I won't go into Agile and describe it and those types of things, and in fact it assumes a little bit more along the lean side. Those that have been through one of the lean classes, you'll recognize a couple of the slides, but for the most part it is relatively new material. One of the things that's interesting is we kind of look at this concept. So I always like to know, why do people come to this session? You had a whole bunch to choose from. Why'd you choose this one? Someone got to give me an answer, and I'll repeat it back. Because what? Catchy title. So I did a good job titling something. You mean you can actually slow down and speed things up? Is that what brought you in? All right, so I did good marketing. What else? What's another reason? I want to make sure I answer these things. Get more done and released, okay? So we're always under pressure in the development environment to how do we deliver all the stuff we're being asked to do? And the short answer is you never will. There will always be more work to do than you can deliver. What we want to focus on is how do you actually deliver what you should deliver? Because there's a lot of requests that come in that, quite frankly, we shouldn't deliver. That they're a one-off request, or hey, that's nice, but if we look at the overall cost of what that's going to cost Cerner as an organization and cost our clients from a support and training and all those other aspects, it's probably a bad idea for us to go do. And so we want to get those things off of our plate to ensure that the things that we should deliver, we now can deliver really fast. All right? So speeding up or slowing down to speed up. So how many of you have heard Aesop or Aesop's fable, however you want to say that term? How many of you have heard that, the tortoise and the hare story? Right? What's the story? We have the hare, which is obviously really fast. But what's the hare do? It runs really, really fast. If you ever gone rabbit hunting or anything like that, or watched the rabbits on the Discovery Channel or whatever, they dart all around. They never go in a straight line. Right? They stop and take a nap when they're tired. The tortoise won the race because the tortoise was consistent and was determined that they were not going to lose. So rather than, run really fast and then have to take a break, just kept at a constant pace. When we talk about Agile software development, one of the 12 principles is we want to promote working at a sustainable pace. If you are working, now I won't ask you to raise your hand, but think of how many of you have worked 80, 90, 100-hour weeks, and how you felt after that, and if you think that's a sustainable pace or not. Or even a 60-hour week, or 3, 4, 5, 6 60-hour weeks in a row. Does that feel sustainable? Right? And again, don't answer the question except to yourself. But the reality is, most of us can go fast for a short period of time. Right? Usain Bolt does not win the mile or the marathon. He wins the 100-meter dash and the 200-meter dash. You put him in a race where he's actually got to sustain, and he is going to lose, even though he's got those big, long legs. So we want to work at that sustainable pace because we're in this for the long haul. Right? Software development is not a sprint. It is more like a marathon. When we look at it from a lean perspective, there's 3 principles that come out of the Toyota way that we want to look at. We want to have continuous process flow because it brings problems to the surface quickly. We want to use pull systems in our models to avoid overproduction in our system. Don't be producing stuff that nobody needs. And then lastly, we want to make sure we level out the workload. Right? If we know a big bulb of work is coming in, a bolus of work, and we got to do something about it, let's staff for it. Let's not just, everybody's got to figure out how to do it. Let's be smarter about it so we can actually deliver. And then one of my favorite quotes it comes from Don Reinertstein, who writes a lot of books on product development and teaches at Cal Berkeley on this topic. We are in this to win the software development game. And the reality is, speed is not what we're about. Speed is a means to an end. What we're really about is winning. And In this case, he says, it's all about money. In reality, it's whatever we value, right? We are trying to get to some value, which is going to be Cerner's mission and vision. That is what we're trying to attain, not going fast. Going fast is an enabler, right? But we don't want to subvert everything in our process just to go fast. So, a couple things, right? We're all going to face this today, and thanks to construction in this area, it's going to be worse than normal, right? We're going to be a car, we want to get on a freeway, we want to get a car off. If the road looks like this, how's the commute home? Right? This is a 2 a.m. road, right? We're pretty excited about this road. I can drive as fast as I want, be Mario Andretti, and I'm happy, right? If the road looks like this and has, 50% usage, still a pretty good commute, right? I can still drive the speed limit or even a little bit above, and I'm good to go. But you populate the road like this, how fast do we go? Guarantee it's not anywhere near the speed limit. How many of you want to kick off a compile when your CPU's pegged? Right? None of us like anything that's utilized at 100%. As a result, but if you look at our development models and how you probably feel pretty utilized at 100%. How many of you have been to India? Experienced the traffic there? Okay. So this is a pretty standard India traffic day. This is not a traffic jam by any stretch of the imagination. We have to understand that in traffic and in development, and it's interesting because development mirrors traffic very, very closely, size matters. Right? If I'm a big bus and I'm in India and I want to get somewhere, do you think I'm going to get there as quickly as someone on a motorcycle? Not so much. And if you've been to India, you'll notice that the bigger the vehicle, the more dents and dings and scratches that it has just to get where it has to go. And even then, they have to be really aggressive to try and get there. But nothing escapes unscathed. Now, interestingly, I was just reading an article that says that the third world countries, which they still count India in that group, third world countries have about half the motor vehicles that are out there in production in the world. And percentage-wise, they have almost 100% of the traffic fatalities that are out there because of driving patterns that look something like this, where we take a road that maybe was meant for 3 lanes of cars, and we pack it full, right? And you'll notice we got, the auto rickshaws, we have motorcycles, and if you're on a motorcycle, you can kind of get around and get through things. If we look at that from a software development perspective, motorcycles are things that quite frankly, don't mean a whole lot. Maybe they're a single CR out of a service, right? They're not something that always adds significant value. The stuff that we say adds value is the stuff that keeps getting stuck. And so the only way that we can unclog the roads is to find a way to remove the stuff that doesn't need to be there, or to find a way to change the speed at which it goes. So, doing traffic studies, most of the time, and we're all going to face this with the way the road construction is around here, most of the time when people encounter a traffic signal that says, let's merge to one lane, how far out do people start merging over? Way, way out. And you know that the police actually don't want you to do that. They want you to wait till the last moment to do the merge. Because if you merge too soon, you slow traffic down way, way faster. The other thing they want you to do is create gaps. So they call it the zipper model, where they want people to go every other car. Well, everybody knows that, we go every other car, but for some reason we think that the person who's in the outside lane, because they didn't merge early like we did, I'm not going to let them in, right? So I'm going to go bumper to bumper with whoever else is in front of me. We're all going to be hitting the brakes, and we're going to be hanging out, and the reality is look at the throughput difference. Easy model. Does it work? Yes. All right. MODOT had some problems, and MODOT is actually, I'll give them some credit, they're actually pretty forward-thinking. In Springfield, Missouri, they have several of these 4-lane overpasses that you have to go over, going over the freeway. And they basically, Springfield's been growing, they basically said, we're growing too fast, we got to build a new one. And they said, well, let's do a case study and see if there's some ways that we can maybe take advantage of the existing structure instead, because they did a cost analysis and found that if I tear down this 4-lane bridge, I've got to rebuild a new one. It's going to cost us $10 million. Let's not go spend that $10 million until we're sure that's the right thing to do. So instead, they looked at some other models, looked over to Europe, and Europe has some pretty good models for traffic flow. And so what they went with is what's called a crossover or double crossover diamond exchange. And there's a couple of these down here in Kansas City now. But it feels really weird to most of us because I'm actually crossing across traffic at a stoplight to go over to the other side. But what it eliminates is the turn light at the back side. So they implemented this in Springfield, Missouri. This was the first one in the U.S. This was back in 2009. You'll see these more and more as you travel around the country because of the results they got. This only cost them $3.2 million to accomplish the same thing. And what they found was that the 4-lane DCD, as they call it, performs as well as a 6-lane traditional interchange. Right? So all they did was figure out a way to take what we had existing, rearrange the work a little bit, and solve the problem. But let's look at some of the other statistics that are up there. Total delay. So this is the time that any vehicle would be delayed was reduced by 67%. So that meant something sat there waiting only 33% of the time of what it had previously. So everybody got faster. Total number of vehicles that had to stop was reduced by 50%. So 50% of the normal traffic that went through never even had to stop. They had a green light through the one light they had to go through, and they just kept going because of the way they modeled it. Capacity, 30% increase. I think we'd all like those 30% increase in our productivity. And then safety was a very interesting one. They did a comparative study between experienced drivers, so they actually did a European model and then one in the U.S. for how well this went, and found that the DCD resulted in, over a 5-year period, only 11 light injury accidents, whereas the traditional model that we have has usually around 23 fatal or severe accidents per year. So safety actually went up, and the reason it went up is because they reduced what are called collision points, and we'll show that in the next slide. But here's an interesting fact. The average speed per vehicle reduced. It went down, dropped 10 miles an hour. So the average speed going through a DCD is 24 miles per hour as opposed to 34 miles per hour if I'm going through and happen to have all green lights going through the traditional intersection. But still, my throughput was worse going at the higher speed. So if we look at these collision points that they reduced and the reason it was so successful, in a traditional model, you have 26 different locations where an accident can occur. By changing the model, they were able to get down to only 14 conflict points, places where accidents could occur. And as a result, increase that safety, increase that throughput. All right? We can think of those conflicts as handovers in our software development process. The more we hand over things, the more we rely on other teams or other groups to do work to help us get a constant delivery, we're having accident points. Because now I have to worry about, do they have this as a priority? Is this actually going to be something they do? Are they going to deliver it the first time right to me, or are we going to have rework after the fact? Anybody driven in a roundabout? Do you like them? Yes? No? Okay. I'm going to adjust my microphone here. There we go. Why do we have roundabouts popping up everywhere? Because they work. All right, so let's take a look at some of the throughput over a traditional 4-lane stop or over a stoplight. Delays reduced by 89%. That's pretty good. Number of vehicles that actually have to stop reduced by 56%. And you'll find that most of your fuel consumption, most of your delays are spent when you do a stop and start. 20% increase in throughput over a 4-way stop. I can handle 20% at load more. And over a 4-way stoplight, 40% more. Right? Pretty good. Now, in addition, some of the other things, safety. 90% reduction in fatalities. I kind of like that figure. of all the accidents that occur, most of them are very minor accidents. They reduce the collision points from 32 possible collision points down to 8. So now I don't have to worry about really getting in accidents. But the next key feature, speed limit is reduced, usually down to about 15 miles an hour that I'm going through these things. We drive a little bit slower through the roundabouts because we're a little bit unsure of them, but we're walking in and it's kind of a yield all the time. So I'm yielding and then I'm going through. Whatever that may be, we're going slower, but we're getting much higher throughput overall. Mythbusters, if you want to look this up, they did a little study. They have about a 10-minute video on YouTube. I thought about showing it, but didn't want to give 10 minutes to Mythbusters. But it is very interesting to watch. And they proved, they ended up getting about a 30% increase in throughput on their study on how they did it. Anybody heard about Google's new car? The driverless car, right? It has no steering wheel, no pedals in it whatsoever, right? You take a look at that picture. I'm not sure I'd want to ride in it, but it looks a little bit like the Tata Nano, but, it works. But I've seen this design. It's been kicking around since about 2009. And one of the ideas here is for working parents. If I want to send my kid to school, I just drop him in the car and give it directions, and it takes him to school. Right? And now you can have your 5-year-old can have a car. Isn't that great? So that's one of the things they're looking at is how can we do this? Their maximum speed limit right now is 25 miles an hour. How many of you are going to run out and buy a 25-mile-an-hour car? Right? I'm not, because I like to drive a little bit faster than that. And they're going to get better at it. But one of the things they have is they have software. And that software determines how it's going to interact with the environment, both with the roads and the conditions and also with the other cars around them. How do you think, or what model do you think they would choose in terms of the zipper model or the I'm not going to let that guy in because he cut in front? Which one do you think the software model is going to choose? So we're going to, if we get to this where we don't have to be driving and allow the computer to drive for us, we're actually going to get much better throughput on our traffic. Now, is that going to happen in 5 years? I don't know. I kind of like to drive, so we'll see. So one of the things that all of this is based off of, and the models that are built into the software systems that Google's using, are all based off of queuing theory. And queuing theory is a whole study in mathematics. There's a whole lot of very complex formulas you'll hear about, and there's some simple formulas like Little's Law that you'll read about and you can go study and we can determine how well things move through our systems. But the reality is we have to understand how things work and how things line up. Now, one of the challenges with software development is that our inventory or our projects in flight are not visible. Right? So it's not like I go to a factory and I can see that stuff is backing up. And I can see that there's visually a problem. And that's one of the reasons why physical Agile boards, be they a Scrum board or a Kanban board, are very effective because I start to see the pileups and the accidents that are occurring. And I have to take some action on it. But without that visibility, queues are hidden. And so one of the things that we'll recommend coming out of this, if you want to go fast, you have to know all the stuff that's on your road. There should be no hidden work. If something's hidden, even if it's just hey, can you look at this really quick, you need to give visibility to it because it's causing congestion on your roadway. We introduced 2 measures that are very important to us. One is lead time. That is the perspective of the client. From the time I have a problem as a client till the time the problem's resolved for me. The other one is cycle time, which is from the time that our system picks up the problem till the time our system has completed the resolution of that problem. Now, oftentimes, those will be the same thing. In our world, however, they are 2 different things. Because if you think about it, from the time we in software engineering, be IP development or wherever it is, by the time we pick up something, how long has the client been experiencing that problem already? And by the time we have it ready for them on a package to deliver and we're saying, I'm done, how long until it's actually installed in their environment and tested and available to everybody to actually use? And so when we look at our class scores and some of those other things, they don't measure us by cycle time. They could care less, right? They measure by lead time. What is my actual user experience? So if we want to get better and be viewed better in the industry, lead time is the thing that we have to pay attention to. And that's one of the reasons why we have the Rapid Broad Adoption initiative that's been going on for the last 18 months and will continue to be out there, because we have to focus on the client view of how our work is delivered to them. The whole goal with a lean model is to not focus on single individual, how fast did this one car get through the system, but look at it more from a traffic perspective. How fast are we in general getting things through? What's our average? And we can build service level agreements off of that and make commitments. If I know that this thing comes in, and let's just say it's a 5-story point thing, and we know that on average it takes our team 2 weeks to get that totally deployed, I don't have to estimate anymore. It comes in, I know it's 2 weeks, we'll get it to you in 2 weeks. And most of the time we're going to hit it, and it'll be rare when we don't. Right? So when you hear about how lean can potentially eliminate estimation, that's how they're talking about it. It doesn't mean you get to eliminate commitment. You never eliminate commitment. We have to build those service level agreements so that our clients, so that we get predictable and build trust. And then the big thing we want to look at is, again, stops and starts. Waiting time is the thing that destroys most of our productivity when we look at any of our measures. If something is sitting in a queue waiting for someone to do something, that will delay. It's like sitting at the stoplight. How many of you want to sit at a stoplight and maybe it flips a couple times for the people going the different directions, and how long do you sit in that lane while your light's not changing? Right? We usually give it one turn. If it goes 2, then we do something illegal. Right? Which is pretty much what we do here too. Right? We have the kill a snake mentality, and I'll let you miss once, right? But if you don't keep your commitment to me as a team, I'm going to go around you the next time, because that's what I have to do to deliver. And as a result, our quality suffers, our clients suffer for that decision because we weren't predictable, because we were tired of waiting. So we want to eliminate that wait time. Some of those mathematical models, when it comes to queuing theory, this is what they come up with when in terms of utilization versus wait time. I can get out to about 40% utilization of a system before I start to incur wait time. And so if you think about that from a freeway perspective, once the freeway gets about 40% full, we start to have to brake every once in a while and pay a little more attention to the traffic around us, so it takes us just a little bit longer. But what happens as soon as we hit that 40%, we start to have an exponential growth. And basically, it starts to double every 10%, the amount of wait time. And the difference between 75% utilization, if a freeway is 75% utilized, and a car trying to get on when it's 95% utilized, it's going to take me 25 times longer to get on that road at 95% utilization than it would at 25% utilization. How many of you think, and again, don't raise your hands, how many of you think you're at 95 or more percent utilization, right? And in most cases, what we find when we develop roadmaps and we manage our software development processes, if you look at the industry in general, most development companies operate at about a 98% utilization model in terms of their scheduling. And you wonder why our industry is thought of not meeting commitments. Right? It just comes down to we're too overloaded to account for any change, right? And change happens. We know it happens. So we have to figure out how do we account for change in the system. It's even worse when we account for variability. So the previous model was a low variability model, so it had a coefficient variation of 1.5. A lot of our work, especially our bigger projects, things like population health or whatever, where we're trying to establish the market and still figure out the direction it's going, our coefficient of variation is much higher. It's probably a 2.5 in this model, which means that at about 40%, I'm already introducing quite a bit of wait time into the system because we're changing projects, changing priorities, whatever that may be. We have to understand these models as we go into our planning. All right, so ways we can reduce cycle time, how long it takes for things to get through the system. There's really 2 ways. You can change the way work arrives into the system. So an example of that would be, I'm going to put stoplights on the on-ramps going onto a freeway, that at peak times, you basically have to wait to get on the freeway because I know if I just let everybody on, it's going to slow everything down on that freeway at that entrance. Right? What we're trying to do there is reduce variability. The second way is we can change the way work is processed, which goes to the high efficiency lanes, the DCD intersections that we showed earlier, roundabouts. Those are examples of changing how work is processed within the system to gain greater efficiency. Those are the only real two ways I can deal with cycle time. Now, the other one that Lean will throw in, oops, went one too far, sorry, is eliminate waste, right? If we have something in our system that is contributing to a waste, we need to get rid of it. And usually that'll happen when we address one of those two factors, changing the way work arrives or changing the way work is processed. So one of the models we use to change the way work is processed is we look at it from what's called the theory of constraints. The theory of constraints comes from a book by Eli Goldratt called The Goal. It's one of those management fable books. It's been popular for about 15 years. But it kind of goes like this. You're a client. We have a client, and then we have a team. The client comes to the team and says, I want something, so we have to deliver it. Right? If it looked like this, we'd be great. The problem is, most of the time, our internal plumbing looks something like this. So what do? We fill in at the level of the input queue, because we want to keep that team busy all the time. It flows downstream, and we look at it, and it hits that bottleneck. And then what happens is physics takes over. Physics says, well, I'm going to reduce my volume that can come out at the level of the bottleneck. It will have a lot of pressure to it, right? Just like sticking your finger over a hose. But the volume of water that's coming out is still the same. I'm not getting any more out. Right? And then we create a backup. Now everything fills up. And now we enter a state where everyone is 100% occupied except for that very last little bit, and it'll never get utilized. And we're still not releasing at a good rate, and we can't figure out why. And so every organization along this chain will go to management and say, I need more resources. I can't get more stuff done. We can't get more delivered. And the reality is if I add resources to any of those first 4 channels, it's going to do no good whatsoever. We're still going to deliver at the lowest rate possible. Right? So what theory of constraints says is reduce your intake down to the level of your bottleneck, and then go fix your bottleneck. And so we would do that by changing the way work arrives in the system. So maybe we take something that was in the definition of done of that 5th lane there and move it into the previous lanes. Right? In engineering world, maybe deployment. I look at it, and most of the studies I've done on Cerner, our deployment process is our bottleneck. And so that's why we're spending a lot of time on test automation and doing things that enable us to deploy to our clients faster. It's one of the reasons why I want to migrate to the cloud as quickly as possible, because we get through a lot of those deployment challenges as quickly as possible. But until I open up that throttle, it doesn't matter how many new engineers I add, because our clients still can't take the code any faster. They still have to go through a large level of testing and training and everything else to get it deployed to their site. So that's why when we talk about develop with the end in mind, we're thinking about how do I open up that throttle so that we can deliver more, so that we can add more engineering capacity and actually get it out and adopted by clients. Once I solve that bottleneck, now I can increase my intake, then I go solve the next bottleneck. So what this introduces is what is called systems thinking. So instead of thinking about things in terms of just my team or my organization, it's what is our value stream end to end? How do we deliver from start to finish, and where are the problems that we need to resolve? And then we take that system and we try and optimize it, right? I want to suboptimize that 5th place. I want to get that place working really, really well so that bottleneck opens up. But everywhere else, I probably am going to leave alone until we solve that problem. So that principle of suboptimization comes to this. I'm a specialist, and each of you are specialists. You're good at what you do. Because of that, you're really fast. As soon as you're done, you hand it over to specialist number 2. They're good at what they do. They're fast too. Hand it to specialist 3. They're fast too. Put it end to end, and we're slow. What we do in a lean and agile model is we purposely take things that used to be done in sequence and we put them in parallel. When I put anything into a parallel system, and you can think about this from RAID disk drives to I was listening to how we move data around. Introducing a RAID system slows your performance overall down, just a hair. but I've got redundancies built in, which help me. Same thing in our development process. We've put things in parallel. As a result, I'm going to increase the communication that has to occur in order for us to move at that speed. This is why we have daily stand-ups and different Agile iteration planning ceremonies, so that we can communicate and keep working together. That's why we have open working environments. Again, so we get some of that communication. As a result, it will slow you personally as an individual down. I guarantee it. Right? You will feel like I'm not going as fast as I could. If you just leave me in a corner and let me code all day, I'd be going much faster. And the answer is, yes, you're right. You'd be going much faster, but we're going slower as a result of us optimizing around you. Right? We are optimizing around how do we develop and deliver to our clients. So I'm going to slow you down. You're going a little slower, but when we put it together, we go a lot faster. Now, when we've introduced Agile, we've gotten about a 30% increase in productivity because of this principle. We have teams that are backsliding, quite frankly. We could be better. And we're going to be doing some things through the Agile Center of Excellence to be able to do additional courses to refresh our Agile knowledge so we can get these core tenets back. But the reality is we have to do things in parallel, and to a degree, just like a roundabout, just like the DCD interchange, have to slow you down just a little bit to enable us to get that higher throughput through the system. All right, so one of the tools we use, we've talked about this, is Kanban. All we do is visualize your workflow, put stuff on a board, limit your work in process, right? So this is how many cars can make it through. This is how many lanes of traffic we want, right? I cannot take a lane or group that has 3 things that I'm allowed, 3 lanes of traffic, and I can't throw 7 lanes of traffic into it, right? You get 3. That's what that road can handle. So that's all we let through. And then we measure and optimize flow. How quickly can I take something from to-do to done? That's all we're trying to do. Corey Lottis was a developer on one of the first teams that used lean software development out of Seattle. He had a book called Scrum. Terrible book, don't read it. But he did have a good quote. He's a developer trying to write a book, and it wasn't very good. But he did have a good book that says, don't build features nobody needs right now. Don't write more code than you can, or don't write more specs than you can code. Don't write more code than you can test. Don't test more code than you can deploy. And I add, for our purposes, don't deploy more code than your clients can take live. Because all we're doing is creating inventories. And nobody's going to be able to use it, but the cost of support and maintenance and training and everything else is still there. One of the other tools we introduce is what's called a cumulative flow diagram. And every time I see one of these diagrams, I pretty much throw up because they look really ugly. Right? Hard to understand, but there's a lot of valuable information here. All this does is basically track over time how many things have entered each queue in your system. So the very top line is just how many things have entered our backlog. The second line is how many things have we started development. Third line is how many things are in test. Fourth is how many are ready for deployment. Last one is how many are actually released. So I can tell some very valuable information about our averages, how long it takes us to do stuff. Our cycle time, from the time we pick up the code to the time it's on a package, I can basically see at any point in time what's our average. How long does it take for one individual item on average to get through? I can see lead time, time it entered our backlog to the time it's deployed in the client environment. That's a very good metric to know. I know how much work we have in process. I know how big our total all backlog is that we haven't even started. I know everything that's within our system. And then there's these 2 slope lines that are really, really important. One is our arrival rate. It's the slope of your backlog. The other one is your deployment rate or departure rate. If your arrival rate is greater than your departure rate, what's going to happen? Right? You're going to enter a state where your queue keeps growing and you're never going to get out. If our team averages delivering 2 CRs a week and we are receiving 5 new CRs a week, guess what? We're never digging out from the ditch we're in. You can use these, one, for helping justify where we need to put additional resources, right? We need to show how are we going to make this better. I've got to get those 2 slope lines at least in parallel. What you're really hoping for is they start to converge a little bit. For teams that are following Scrum, if you're not following Kanban, you can merge the 2 boards together. I can use Scrum at a high level for capabilities, and I can use my Scrum at the low level for stories, and tasks, and then Kanban at the top level for capabilities. Right? They work well together. That's actually how we manage a lot of our portfolio development at Cerner, behind the scenes. So one of the other things I want to call out is the economics of fast feedback. In this scenario, we have a $100 lottery ticket that you can buy for $1, and payout is $100. Option 1 is I buy a ticket, and 99 times out of 100, I'm going to get nothing. One time out of 100 on average, I'm going to win, which means my average payout is going to be 0. Right? It's going to cost me $100 to make $100. The other thing we can do is say, you know what, let's break this down a little smaller. I'm only going to buy the first digit in the 2-digit lottery for 50 cents. 90% of the time, I don't have the right digit. So guess what? That cost me 45 bucks. Right? So I'm out $45, my payout is 0. 10% of the time, I'm going to go ahead and buy the next digit. So that costs me another $10. But 9 times out of 10, I still get nothing. But 1 time out of that 10, I'm going to win. My total cost, however, this time is only $55, so I'm actually going to make $45 out of this transaction because of the feedback logic. We want to make sure that we are breaking our development projects down small enough that we can take advantage of some of this fast feedback, that we know when we got it right and know when we need to make some adjustments. Buy that first digit instead of buying the whole lottery ticket at once and just hoping we win. So now what? Right, so to wrap this up, how do I focus on delivery? First, your team needs to sit back and figure out how do you deliver value to the client, start to finish. Tool we use in Lean is called value stream mapping. Again, we teach a class on this, so we can take you through in detail. Second, you want to be able to synchronize your work with the entire value stream delivery. Right? So you want to make sure that testing and deployment and everything else are actually working together rather than against one another. We use the value stream mapping, and then a Kanban board helps visualize that. From there, you've got to figure out what your team's speed limit is. Don't try and take on more work than you have capacity to do. Lastly on this slide, break things down. Remember, size matters. Smaller the better. Next thing we need to do, slow you down. Right? Figure out how to eliminate those stops and starts. Use your Agile planning ceremonies effectively. Work together as a team. Do cross-functional training so if testing is having a problem, people can go help. Right? Rather than, well, that's not my job. Make all of your work visible. This is one of our chief challenges at Cerner. For teams that we've gone and measured this on over the last year or so, we found that anywhere between 30 and 50% of what teams do in the current iteration was not planned in the beginning of the iteration. They're picking stuff up from side projects, or someone sent them an email or an IM or some escalation or whatever that may be. That's okay if that's how we're going to operate. I don't like it too much, but if that's how your team wants to operate, fine, but make it visible so everybody knows why you're not meeting your commitments, because I guarantee you you're not. From there, control your input queue. This is probably one of the hardest things to do. If I cannot control what's coming in to a degree, or at least plan for it, it's very hard to react. There's going to be always some variability, that's okay, but I've got to know what my arrival rate should be over time on average. Understand and plan for that variability. Variability is not bad, it just needs to be somewhat controlled. And then lastly, measure and optimize flow through your system. All right, so we only have 2 minutes for questions. What questions do you have? And I'm sure I won't be able to answer them all, but I can answer what I can in the time period. Unless you have no questions, it's a perfect presentation, which I doubt.
I have a question.
Oh, okay.
You talk about how we need to slow down to speed up and eliminate wait times.
Yep.
But you also say that we want to parallelize. Doesn't parallelization introduce new wait times?
That's an interesting concept. So what I would say is no, because what I would do is organize your team so that your parallelization is done within your team as much as possible. Again, going back to wanting to reduce the number of collision points that occur, we need to have some structures between teams or groups of teams that enable them to work together. But yes, if all I do is parallelize 3 teams that really don't care about each other and try and get them to go faster, I will actually delay the system more. You're correct. Okay.
My development team is on the Jira-based system of doing units of work.
Okay.
Tooling available to us?
Okay, so the question is, we use Jira as a tool. Is there any tooling available to help us envision and do this? Jira actually will support this. You have to do some linking, and if Shazad Zafar or Adam Klein are around, you can contact them around how we've done it for Project Go and for Millennium Plus. But you can support this. This is fully supported in Jira. It's better supported in version 1. And in some cases, you can mix the 2 tools. You can use version 1 maybe for your high-level planning. It deals with these levels of connectivity much better. And then Jira for your task-level work that the engineering does. We have integration tools that enable us to do that. All right, so we are out of time. I'm happy to talk to anybody over on the side. I will make the slides available, and then I have to give the plug for please fill out the card and put it in the hat or the bucket as you go out.